Ever notice an AI answer starts slow then suddenly speeds up? That's not your imagination, and it's not the model warming up. The simple answer is the KV cache. The model spends time up front processing your entire prompt, saving compact vectors for every word. Once that's cached, each new word can be generated by reusing what's already there, which is much cheaper. So it feels like the system hits the gas mid-sentence. Here's the key idea in plain English. There are two phases when a transformer model replies. First, a slow prefill phase that reads your prompt and builds the cache. Then a much faster decode phase that writes the answer one token at a time by looking up what's in that cache. The speedup isn't learning on the fly, it's just not doing the same work twice. A quick myth to retire early. AI does not adapt or figure you out mid-answer to go faster. The speedup comes from reusing saved work, those key and value vectors, not from the model improving itself during the response. Think of it like a book with a great index and highlighted notes. First, you read the whole chapter and build the index, slow but done once. After that, when asked a question, you don't reread the chapter. You flick through the index in your highlights and answer quickly. That index and those notes are the KV cache. What matters here is how the model looks at context. Transformers use a mechanism called self-attention. In other words, each word creates three small vectors, a query that asks, "What's relevant to me?" and a key and value that summarize each prior word. During prefill, the model converts every token in your prompt into keys and values across all its layers and attention heads. That's the expensive part because everything compares with everything. Compute grows roughly with the square of the prompt length. Put differently, prefill is a big one-time cost. The payoff comes immediately after. During decoding, when the model generates the next token, it only needs to compute the query, key, and value for that new token, then compare that query against all the keys in the cache. That's linear work, not quadratic, so it's dramatically faster. The model appends the new token's key and value to the cache and continues. That's why streaming feels smooth and, after the first words, often feels almost instant. Let that sink in. Most of the time you wait is before the first word of the answer. To make this concrete, imagine a 7 billion parameter model generating a 50-token reply to a 100-token prompt on a single GPU. Prefill might take around 200 milliseconds to process those 100 tokens. Then each new token in the answer might take about 2 milliseconds as it reuses the cache. So you get the first words after that initial 200 milliseconds, and the rest flows quickly, on the order of a couple of milliseconds per token. Without a cache, the model would have to keep reprocessing the entire history for every new token, which would be orders of magnitude slower. There's a beautiful practicality to this design. A small, simple memory, those keys and values, unlocks a huge speed boost by avoiding recomputation. Engineering elegance often looks like this. Do the heavy lifting once, then reuse it relentlessly. Now for the trade-off that matters in real systems. The cache lives in fast memory, and it grows with every token. Memory, not math, is the bottleneck. Each token adds keys and values for many layers and heads, and that footprint scales linearly with context length. With long chats or documents, the cache can reach hundreds of megabytes and beyond. At 16-bit precision, expect roughly single-digit megabytes per thousand tokens, and for long contexts, totals around a gigabyte are common. On a busy GPU server, that eats into how many users can be served at once. That's why long conversations sometimes feel slower and cost more. The model must keep the entire conversation's keys and values alive to answer based on that history. If memory gets tight, servers reduce batch sizes, evict old sessions, or truncate context. All of those choices affect latency and cost. Here's where infrastructure tricks come in. Providers often batch requests that share a similar prefix to amortize the prefill. If 10 users start with the same system prompt or first paragraph, a smart server runs that heavy prefill once and fans out the results. Projects like VLLM also use paged attention, which organizes the cache like virtual memory so it can pack and move chunks efficiently instead of copying massive blocks around. Streaming is another experience boost. Even though prefill may dominate for a long prompt, streaming starts sending tokens the moment decode begins. Humans perceive progress, which feels faster than waiting for the whole answer to finish. The underlying compute hasn't changed, the delivery has. There's also quantization. Many deployments store the KV cache in reduced precision, 8-bit or mixed precision, to fit more context or more users into the same VRAM. That doesn't change the algorithm, it just shrinks the memory footprint with little quality loss in practice. On consumer hardware, tools like llama.cpp lean on these optimizations to make local models feel responsive even without a big data center. A subtle limit trips up new builders. The cache is tied to a single sequence. Start a brand new prompt and there's no reuse. You pay prefill again. And if a conversation branches or you edit earlier text, the model may need to recompute portions because those earlier tokens changed. It's like updating the index after adding paragraphs to a chapter. Some of the earlier shortcuts no longer apply. So how should this shape prompts and apps? The simple version is, keep prompts lean and keep what's stable. Try to avoid dragging full conversation histories forever. Summarize old turns into a short digest that preserves the facts and tone, then continue with that summary instead of hundreds of raw lines. This preserves relevance while holding the cache size in check. In a chat product, that can cut memory use by large margins while keeping answers on track. Another practical move is to measure. Many inference servers expose timing for prefill versus decode. If logs show prefill dominating, trim boilerplate templates or repeated instructions. If decode is slow, the model might be underpowered, starved of memory bandwidth, or throttled by too many concurrent sessions. Knowing which phase eats time points to the right fix. On the back end, grouping similar task types pays off. If most support tickets start with the same instructions, route them together. Shared prefixes let the server reuse the heavy part so more throughput fits into the same hardware. This is why template design matters. A consistent, compact system message is not just tidy, it's operationally cheaper. The core mechanics are straightforward once the pieces are named. Keys and values are compact summaries of what each pass token offers. A new token forms a query that says, which pass pieces matter to me right now? Multiply queries by keys, get attention weights, blend with values, predict the next token. Prefill computes those offers for the whole prompt once. Decode looks them up cheaply, token by token, and appends to the cache as it goes. There's an understated bit of wonder here. The model writes by constantly rereading its own memory of the conversation, but because that memory is organized as keys and values, it can do that rereading with remarkable efficiency. A tiny design choice, what to remember and how to index it, translates into real-world speed that people feel. In production, this explains familiar quirks. Long policy blocks at the top of a prompt? They make the first token slower and inflate memory for the entire session. Pasting a huge PDF? Expect chunky prefill time. But once the answer starts, even a modest GPU can stream text briskly, because the model's just scanning and adding to its cache as it goes. It's the same reason a fresh chat often feels snappier than a sprawling one. The cache is smaller, so both prefill and per-token attention are lighter. Two final misconceptions to clear out of the way. The KV cache doesn't reduce the number of model parameters, and it doesn't make training easier. It's purely an inference time trick, storing intermediate results so generation can skip redundant work. Also, it's not a general-purpose cache that can be shared across unrelated prompts. Each conversation builds its own memory because context is specific. So the takeaway is crisp. AI feels like it speeds up mid-answer because it does the expensive thinking once, then reuses that work for each new token. The KV cache is the index and notes that make that possible. If responsiveness and cost matter, keep prompts tight, summarize history, and lean on streaming. On the server side, batch shared prefixes, monitor prefill versus decode, and consider lower precision caches to fit more users. Small architectural choices up front cascade into a faster, cheaper, more reliable experience. If this helped make the mystery feel simple, consider subscribing for more clear, no-jargon explainers on how modern AI actually works.